speaker is Elchanan Solomon, who is a graduate student at Brown. He's graduating this year. His advisor is Jeffrey Brock, but he also works with Steve Oudot. And today he's going to tell us about his exciting work, an intrinsic persistent homology transform. Thanks, Elchanan.
Wonderful. Thank you very much, Sarah. So I know I have roughly 50 minutes, but I don't think it'll take that much time, so there should be plenty of time for questions if necessary. Okay, so let's get started. So the general framework of this talk is going to be about, well, it sits inside the general area of inverse problems in TDA. So in TDA, we have many invariants which are stable, functional persistence, zigzag persistence, etc. But you can also ask about the inverse problem. And the inverse problem is really about how discriminative the invariants are. In other words, can you construct invariants which are injective or near injective so that the pre-image is maybe a small collection of shapes which are all similar to each other? And related to that is the pre-image problem. Suppose I give you an invariant and I know it comes from a shape or maybe many shapes. Is there some way to reconstruct it? So these questions are related to issues of explainability and interpretability in machine learning, and this is one way of understanding these questions in the context of TDA. So let's get started with that. So our focus is going to be on the question of injectivity, but actually Steve Oudot and myself have a survey that will soon be in the proceedings of the ABLE Symposium, which discusses inverse problems in TDA in more detail and will include a lot of the things we talked about today. So you can look for that if you're more interested. All right, so I'm going to start going straight into the math. So one recently studied and very interesting invariant in TDA about which inverse results are known is the persistent homology transform, which was defined by Turner et al. First in 2014. And so here's a picture. I'll explain what the picture is showing us. So we have some simplicial complex. It could be more general, but in this setting, let's say we have some simplicial complex M, which is embedded in Rn. And for every direction, every unit vector on the sphere V, I can think about the function on the shape M, which is taking the dot product with V. In other words, you can think of it as a shape and you're sweeping along the shape in the direction of V. And that gives you, well, you can take functional persistence for that function and that'll give you a barcode. And you can do that operation for not just one vector, but really every vector. And so here's a more formal definition in another picture. This is a 2D picture. We have a letter. So this is taken also from the paper by Turner, like the previous picture. And we have a bunch of different directions. And by sweeping along the picture in these different directions, we get these different barcodes. And there is a way to vectorize this operation. So as you sweep in the direction of the vector V, you can look at the persistent homology, but you can also just keep track of the Euler characteristic of the sublevel sets. So in that case, you're not really keeping track of the different dimensions of the homology, and you're also not keeping track of the pairing. So you have a lot less information, but in return, you're working with a function, with a vector. So it puts you in a Hilbert space and makes this invariant a little bit more tractable. So I have some code up on GitHub that produces some of these curves for 2D images. And so here's an example on the left of a letter from an Indian alphabet. And then on the right, the Euler characteristic curve of sweeping, I think in the direction 1, 1, which in this picture is going to be down and to the right. And then I also have a smooth version, that's the orange one, if the colors show up correctly, which is I get from convolving, which would be a bit more stable in theory. So the PHT and the ECT are two invariants that you can compute for shapes embedded in Rn. And let's be clear, we're considering all the vectors on the sphere at once. So the PHT, the transform, starts with a shape and gets a function whose domain is the sphere and whose codomain is the space of barcodes. So it's a pretty complicated object, the full PHT. And the ECT, the Euler Characteristic Transform, is the same idea. For every vector, you get an integer value function. That's what z to the r here means. So it's a little simpler, but still it's a very complicated object because it's indexed over every direction in the sphere. And if the shape is embedded in high dimensions, then we're talking about a high-dimensional sphere. So what do we know about these invariants? So in the original paper, Turner and others, the other authors, demonstrated that in dimensions 2 and 3, that's the dimension of the embedding of the shape, that these transforms are actually injective, both the PHT and the ECT, and they have an explicit reconstruction algorithm. And then later work by Greist and others, and also by Curry and others, including Turner, they use a result of Shapira to prove injectivity for actually all dimensions D, and the proof is really elegant. It just uses Euler calculus, and it provides also a way of getting an inverse. In other words, once you're given the transform, how to rebuild the shape. So in addition to questions of injectivity, you can go onwards and ask, how many directions do I really need to compute to get this injectivity result? Because we have observed that these invariants are really complicated. Do I really need to probe every direction on the sphere? So there are
Isaac, a quick question. So
Sure.
in the reconstruction results where they're using all directions, are they dealing with sort of finite complexes, finite simplicial complexes,
So
for example,
actually-
as their shapes?
Actually, no, it's quite general. It's in general for sub-analytic sets.
Aha.
So
And they show injectivity, but they also are able to reconstruct this sub-analytic set.
So the injectivity result is they demonstrate how to provide an inverse transform.
Aha. Uh-huh.
So the inverse transform, so you get injectivity by providing the inverse. So that's
Right.
actually the logic.
Got it. Thanks.
So that's a really good point because the injectivity result is very general for these sub-analytic sets, but the finiteness results in general are for simpler objects. So let me talk about the two results that have been shown. So Benton et al. Recently showed that if you have a linearly embedded graph, that there is an algorithm for reconstructing the graph from its Euler characteristic transform, and the number of steps is roughly quadratic in the number of vertices in the graph. And so in the process of the algorithm, it ends up only probing finitely many directions. And the complexity isn't too bad. It's just the square in the number of vertices. So Curry et al. In the same paper in which they have some injectivity results also talk about some finiteness results. And those results hold in all dimensions D, but they have to be for linearly embedded simplicial complexes, is my understanding. And unlike the result for planar graphs by Benton and others, it doesn't just depend on, say, the number of vertices or the number of simplices. It depends also on the geometry of the embedding. And the constants as a whole kind of blow up as the dimension goes up. So it is exponential in the dimension. But at the same time, they do have finiteness results that cover infinite families of linearly embedded simplicial complexes. So as long as that complex satisfies certain constraints on the geometry of the embedding, there's a bound on how many directions you have to probe in this reconstruction algorithm. But at the moment, I don't think there's any general finiteness results for more complicated kind of embedded shapes. There's also, I want to just briefly mention, this is an application by Crawford and a host of others. It's a really interesting work in which they apply the Euler Characteristic Transform, or more particularly a smooth version of it, to build a predictor for patient outcomes with a particular kind of a brain tumor, and which ends up being, outperforming certain other predictors based on genomics or other shape descriptors. And so here's a picture I took from that paper. You see that for these types of brain tumors, the topology is really quite interesting. They have all these voids, because this is a 2D slice, they have all these voids inside them. And the ECT and the smooth version is able to capture that and use that information to build a good predictor. So this is an example of an application of the invariants we've seen so far. All right. So now let's talk about the focus of the research that I've been working on with Steve. And the question is there a way to generalize this for an intrinsic metric space? So it's not, you have maybe a graph or something, it's not embedded anywhere. Is there a way to do a similar construction that might hopefully be injective by capturing many different persistence diagrams or barcodes, however you want to think about it, from many different functions? So here's how we're going to do it. There's not necessarily one best way to do it, and I'll talk about other possibilities at the end, but here's a kind of straightforward way. So you start with an intrinsic metric space, and then for every point in that space, you get a function, which is just the distance to that point. And that gives you a family of functions on your space indexed by the space, because every point gives you a function. Now, instead of taking the ordinary sublevel set or superlevel set persistence, we're actually going to use both and combine them together. So this is something called extended persistence. It was defined by Cohen, Steiner, and others. And there's a link at the end to the full paper. But let me take a detour now and explain what extended persistence is before I talk more about the generalization of the ECT. So what is extended persistence? So suppose you have a topological space with a nice real valued function. So for more details about this, read the relevant paper by Cohen Steiner. And I'm going to use the subscript and superscript to denote sublevel sets and superlevel sets. So you end up getting a sequence of topological spaces. So the first sequence on the top row is a sequence where alpha is less than beta. So it's an increasing sequence of sublevel sets. At a certain point, you exhaust the space, so you end up with a full space. And then you switch to looking at pairs of spaces. You think of the space as being the pair of the space and the empty set. And then in the second half of the sequence, you modify the second element of the pair by getting larger and larger superlevel sets. And then eventually you end up with the largest superlevel set, the whole space itself, and you end up with the pair XX. So there's kinds of two parts to the sequence. There's a part which is growing in the sublevel set, and there's also, when you do the homology of the pair, you can kind of think of it as you're collapsing larger and larger superlevel sets. And you can apply homology to this full sequence and still get a barcode decomposition. So I have a not so high-tech visual demonstration of this. So imagine this is a metric space, like a graph with a metric, and there's a height function, and in this case it might be the distance from the node all the way at the bottom. And so the red will indicate these increasing sublevel sets. So the first half of the filtration, you increase the sublevel sets to get the full space, and then the next part you start quotienting out by bigger and bigger superlevel sets. So you should imagine that everything contained in the blue translucent region is collapsed to a point. So if you collapse that, nothing really interesting happens topologically. Now some things will actually happen. I don't know if you can see the mouse, but we end up having a loop because this ends up being a loop in the space because of the gluing. So new topology is introduced, and you collapse more and more and more, and eventually everything dies because you end up collapsing the whole space. And so what's nice about extended persistence in particular, there are no infinite bars. Everything which is born will die. Anyway, which is an interesting thought. Okay, so here's an example of a visualization of all the bars that you can get from this picture. So it's color-coded. So the red one here is the zero-dimensional homology. That's just going to give you the diameter of the space from this point, if you're looking at the distance function, or just the largest function value. The ordinary homological features correspond to the loops that appear in the first half of the sequence, the ordinary half. And you see there's a loop here. There's sort of two loops. Now, the yellow bars correspond to relative homology. Those are things which are born on the way down. So, for example, you can imagine, say, at this highest yellow bar, when the collapsing reaches here, then you end up with a loop. Oh, oops! You end up with a loop which starts here, goes down here, and over here you end up at the same point. So you see that you get a lot more information this way. And in particular, if you started with a tree and you look at the distance from a point, the homology of a tree is always trivial. So you're not going to get any information. But in the relative homology, you get a lot. So you kind of need to take the full extended persistence to get all the topological information. And also, for purposes of stability, it helps to get rid of these infinite bars. So that's extended functional persistence. So let me just go back again to this definition. For every point in my metric space, I'm going to look at the distance to that point as a function and calculate its extended persistence one more time and get the output barcode. And I can do that for every point in the space. And so I get a map psi sub x from the space x. In other words, you put in a base point and it gives you a barcode. Now I'm going to let the Intrinsic Persistent Homology Transform, the IPHT, be the image of the map. And the reason is that I don't want the map to be indexed on the space, because the whole purpose of the invariant is that I don't have to, have the full space. So by taking the image of the map, I get a subset of barcode space regardless of the space I start with. That way the invariants can be compared, because no matter if I have x and y different spaces, I want IPHT of x and IPHT of y to sit in the same ambient space. So standard stability results prove that the map psi sub x is continuous. So when x is compact, its image, its intrinsic persistent homology transform, is a compact subset of barcode space. So this is the definition of our invariant. And for the rest of the talk, for the purposes of stating results, I'll be focusing on the case of metric graphs. So these are metric spaces which underlying are homeomorphic to graphs. You can think of them as graphs with edge weights and the induced path metric. So there is some prior work done here. This is by Day, Shun, Wang in 2015, and they investigated it in a slightly different focus from what Steve and my work, but it's very related. So one of the things they were interested in that paper, or the main focus, was defining a new distance on metric graphs, which is called the persistence distortion metric. And the way it's defined is as follows. You take two metric graphs, you apply the intrinsic persistent homology transform to get two compact subsets of barcode space. Now, the space of compact subsets of a space has a metric, the Hausdorff metric. So now that you have these two subsets, you can compare the Hausdorff metric, and you use the Hausdorff metric, in this case, induced by the bottleneck distance. So this gives you a way of getting a sense of distance between two metric graphs. So how is it related to the Gromov-Hausdorff distance, which is somehow the best studied usual metric that you use to compare metric spaces? Well, you can prove a stability result. They prove that there. It's almost 18 times the Gromov-Hausdorff distance. And they prove that it is exactly computable in polynomial time. And moreover, it's pretty straightforward to approximate. You just have to take a sampling of the points on the space. which is in contrast with the Gromov-Hausdorff distance, which can be NP hard, or in general is NP hard to even approximate. So this is something which is, in a sense, stable. You can relate it to the Gromov-Hausdorff distance, but is much more tractable in terms of computation.
And Isaac, a question there. So
Sure.
is this for any homological dimension of interest?
So these are for metric graphs.
Uh-huh.
So the information is just 0 and 1 dimensional. I mean, it's really mostly 1 dimension, actually.
Okay. And I see. And so they're only looking at one-dimensional homology, or maybe they're
Yeah, so the focus in the discussion of metric graphs is pretty much just 1 dimension. I mean, you can also, you do also keep track of the 0 dimension, but there's really only one piece of information. We're assuming.
I see.
Yeah. So
I see.
Yeah, most of the data, and of course you could generalize this and to a more interesting space, like a high dimensional space, and you get more. But for the purpose of these results, everything is 1 dimensional.
Okay. Thanks.
So one thing I should say is that right, the next bullet point is that actually this transform is unfortunately not injective, which means that the stability result only goes one way. It's possible for the Gromov-Hausdorff distance to be positive. In other words, the two metric graphs are not isometric, but the persistence distortion distance is 0 because their image is exactly the same. And in my paper with Steve, we also found an example of this. It's a pretty simple example of two graphs which have the same transform. And I think if you look at the paper and you stare at it long enough, you can convince yourself that's true. But you can also convince yourself that these graphs have to be chosen very specially to make this work out. So even though we've seen that it's not injective, these counterexamples, at least so far, seem quite special. So the hope is that maybe the failure of injectivity isn't so bad. Could it be a measure 0 phenomenon, or maybe, on some generic set, it's still injective? That would be the hope. And so the next couple slides will be about the different injectivity results we have. So I'm going to start with local injectivity, and then I'll talk about global injectivity. So local injectivity is that for every graph, there is a little ball in the Gromov-Hausdorff metric, such that all the other graphs in that ball have different intrinsic persistent homology transforms. So in other words, you can't have arbitrarily close to a given graph another graph with the same IPHT. So for global injectivity, what we'd like to do is, so we know in general that it's not injective on the full space of metric graphs. Let's find some subset on which it is injective, and hopefully show that that subset is very large, dense, maybe generic. So I'm going to define Inj sub psi to be the set of graphs for which the map psi x is injective. What this means conceptually is that every point gets a distinct barcode. So no two points on the graph, the associated functions have associated functions who give the same barcode. So the first result you can show is that if you restrict yourself to this subset of graphs for which the map psi is injective, then in fact the transform is injective on that set.
In Isaac, so you're in Inj sub phi those are all the graphs where at each point all the persistence diagrams you get at different points are different.
Exactly.
And
so
then now you're talking about IPHT, which is looking at the union of all the barcodes you get, and you're showing that IPHT is injective on this subclass of graphs.
Exactly. So there's two injectivity statements here. There's a subclass of graphs which are defined using an injectivity of the map psi defined on that graph, and now an injectivity on the space of this subset of the full space of graphs. Exactly.
Mm-hmm.
So what's the proof? So the main step of the proof is to show that the map psi sub x is a local isometry in a particular sense, meaning that the nearby points, the distance between the points and the distance between the associated barcodes is the same. As a whole, they're not going to be equal, but locally they're the same. And moreover, when the map psi sub x is injective, because you have a continuous map from a continuous injection from a compact space to a Hausdorff space, you get a homeomorphism. So here's a picture from one of Steve's talks. You start with an initial graph, and then you can think of its image in the barcode space visualized on the right. So it's a homeomorphism. The topology is preserved, but the geometry is not preserved. It could be warped. But you know that the geometry on small scales is the same. So if you take the intrinsic metric, which is the metric you get by connecting together, the local information, you end up reconstructing the original graph. And so that's the injectivity result, an explicit way of rebuilding the graph from its image, from its transform. Right, but of course here it's crucial that psi sub x be injective, because otherwise the topology of the image could change, and you don't know if a new loop shows up. Did that really exist in the original graph? Was it an accident? It's hard to say. So now the question is, we've discussed this, or rather we found this set on which our transform is injective. Is this a big set? It's not going to be very helpful to us if it's only a few graphs which satisfy this condition. So the first result is that it's dense in the Gromov-Hausdorff metric. So in other words, every graph can be Gromov-Hausdorff approximated by another graph whose map psi is injective. And the proof of this is something which we jokingly call Cactus Ocation. So what you do is you take a graph, you insert a bunch of small thorns of different lengths along the edges in such a way that it breaks up all the local symmetries or similarities, and it provides enough different local information that every point ends up having a distinct barcode. So, right, so that's the first result in our direction, that it ends up being Gromov-Hausdorff dense. However, you might hope the next step is that it should actually be, this is also an open set, so it's dense and open, in other words, generic. But in fact, the two counterexamples from earlier, G and H, let's see if I can get back to them. What you can do is you can shrink down these counterexamples and embed them in any other graph. And then the two graphs you get, you can show have the exact same IPHT. So in that sense, you can embed these counterexamples in any Gromov-Hausdorff ball. Because the Gromov-Hausdorff metric just cares about the geometry. It doesn't penalize you for increasing the complexity of the graph by adding a whole bunch of new vertices and edges. So because you can embed these counterexamples in any graph, there's no hope of this subset being generic, because you can find counterexamples in every Gromov-Hausdorff ball. Which tells us that in a certain sense, the Gromov-Hausdorff topology might not be the right topology to frame an injectivity result here. And we're going to look to a slightly different topology on the space of graphs, in which we can say something more. So a slightly finer topology with more open sets. So this is the fiber topology. It has a bit of a long definition, but I'll just explain the definition. So the idea is, how can I index the space of metric graphs? So first of all, there are finitely many combinatorial graphs. That means graphs without any metric information. And I'm not going to include in my graphs any valence 2 vertices, because you can remove or add such a vertex without changing the topology. So you'll end up double counting the same topological type of graph if you do that. So for a fixed combinatorial graph, you can put a metric on it by picking edge weights. So you can think of that as a vector in R to the E, where E is the edge set. And of course, everything has to be, all the entries have to be positive. You can't have any negative distances, or 0 in our case. Now, you also might end up double counting, because if the graph has any symmetries, then different collections of edge weights end up giving you, end up giving you isometric graphs. So you have to quotient out the Euclidean space by the action of the automorphism group permuting the entries. And if you do that, you end up the resulting Euclidean fan completely parameterizes all the distinct metric structures on that combinatorial graph. And if you do this for every different combinatorial type and you take the union, you'll end up having parameterized all possible metric graphs. So in a sense, this parameterization has two parts. There's a combinatorial part, and then once you pick the combinatorial type, you have to pick the edge weights, and to cancel out the symmetries, you have to quotient out by the automorphism group. So this, so I'm going to let omega be this disjoint union of all these Euclidean fans, one for each combinatorial type, and I'm going to topologize each Euclidean fan, each copy of R to the E mod out by the automorphism group, by the quotient topology from the L2 metric on Euclidean space. And then I'm going to give omega the disjoint union topology. What does this mean intuitively? Intuitively, it means that different combinatorial types, they live in different fibers, and there is, in a sense, a certain cost associated. So this doesn't come with a metric, but you could put a metric on it. There is a certain cost associated with adding complexity to the graph. You can't, in this topology, you can't add a loop to a graph and shrink it. It won't converge to the original graph, because once you do that, you end up you're in a different open set. So in this sense, this is why this might be the right topology to talk about this, because it doesn't let you embed these counterexamples into every other situation. All right. So in this topology, we do have a genericity result. And it says that in the fiber topology, so that's the name of this topology because it has a fiber for each combinatorial type, the set of graphs whose map size injective is both open and dense. So how does the proof of this work? You show that if the map, so it's by a contrapositive, you show if the map size is non-injective, then the multi-set of edge lengths of X, in other words, if you think of it as a vector of edge lengths, or just the multi-set of edge lengths, has to be linearly independent over Z. So in other words, this set, Inj sub psi, it contains the complement of all these hyperplanes, which are described by these linear edge relations. And that is in each fiber an open and dense set, and thus in the disjoint union topology an open and dense set. I should also add, as a technical subtlety, this doesn't always work. There are certain graphs certain combinatorial graphs, which regardless of the edge weights you choose, the map psi will never be injective. And the reason is, imagine, for example, you have a graph with a self-loop attached. There's always an automorphism that flips that loop. It just reverses the orientation. And when you have an automorphism of your graph, any 2 points exchanged by the automorphism give you the same barcode. So a graph with a non-trivial automorphism group cannot have psi be injective. Although just because the automorphism group is trivial does not imply that psi is injective. So this is a more subtle condition. So anyhow, in these subtle cases, like when there are these loops, you have to slightly modify the theorem, but the same result holds. And the last thing to say is that the stability and injectivity results that we've been talking about for the IPHT, there's also a version that includes measures. So you start with a graph, a metric graph, which also has a measure on it, and you push forward the measure onto a measure on the subset of barcode space, and you can ask, can you recover the metric measure space? And the same more or less results hold with some minor changes. All right, so you might have muted yourself actually.
Oh, sorry. A question there. So on the I have this metric graph, and now I have a measure on it, and so in some region, some local region of the graph, I have a mass associated to that region. And then I produce the barcodes for that region of the graph. And then I push forward the measure so that I have a mass associated with those barcodes.
Exactly.
Is that right? Okay.
Yeah. Although, so there are some restrictions. Generally, we would want the measure to have full support. Because then otherwise you might, if it doesn't have support, then that half the graph will just disappear in the image because there's no measure there, and then you can't recover that. So, but assuming that it has full support, exactly, that's a situation. You push forward it onto a measure on barcodes.
And then on the graph side, you have this metric measure version of the fiber topology, and then on the IPHT side, do you have this instead of the I guess there you're using the Hausdorff distance. Are you using sort of this Wasserstein distance?
Yeah, so there are different ways of generalizing the Gromov-Hausdorff distance to measure cases, and there's some work by Facundo on this, and I use one of the ones that Facundo develops. Yes, you have to use some appropriate version, modification of Gromov-Hausdorff for metric measure spaces.
Very cool. Thanks.
Thank you. So let's talk. So that's the results. Let me talk about the current work. So just like in the embedded case, there's an Euler characteristic version. You could try to do the same thing in the intrinsic version. There are many different ways of setting this up. Here's one that I think is a good one. So so instead of psi, I'm going to take this sort of fractor x, and what you do is you take the usual IPHT, so you get these collections of bars, and then you look at the associated characteristic function, and then you just sum it again with the sign coming from the dimension. So this is a way of vectorizing it. Of taking the IPHT and producing a function using the characteristic, or I should say the indicator functions of the intervals in the barcode. So the questions are, can you get stability results? So the usual kind of stability results won't exactly hold, but what kind of stability results can you get for a transform like this? So the reason you won't have the usual stability results is in the Gromov-Hausdorff sense, you can add a little loop to a graph, and it's very similar to the original graph, metrically speaking. And it doesn't matter how many loops you add. You can add literally a million, or as many as you like, tiny little loops to a graph, and you'll end up with something very close to the Gromov-Hausdorff distance. And in the barcode, you get a bunch of points near the diagonal. But in this situation, those little loops, these little bars, will actually add up, and so they can really perturb the function a lot. So you're not going to get Gromov-Hausdorff stability in that sense, although maybe you feel like adding a million small loops to a graph should make it very different, in which case maybe that isn't such a bad idea. But as a whole, there are some stability challenges about what kind of metric you want to use, how to compare these vectorizations to make this a stable invariant. And there's also the question of injectivity, which is this injective like in the same sense, in the same generic sense of the IPHT? And at the moment, I think that, we think that it is likely that the same results hold, and you just have to adjust the proofs a little bit, some extra casework, and this is currently work in progress.
Isaac, I was wondering if you could walk me through the definition of this chi-g again. So these D's are just non-negative integers, is that right?
Right. So maybe the way to visualize it is you have the barcode. So you have all these. Now think of it as bars. And
so capital I is a bar, is that right?
Exactly. And then the little D subscript should denote the dimension.
I see, the homology dimension.
Yeah, I should make that clear. That's a good point. And so I'm going to sum the indicator functions of all of these intervals. with a sign coming from the dimension.
So this is going to be so when you sum all these indicator functions, you get a function.
I missing?
You get a function which is integer valued, a real integer valued function on the real line.
I see. So if I had two bars that were overlapping like this, like the sum of those indicator functions would look something like 0, 1, 2, 1, 0.
If they're in the same dimension, yeah.
If they're in the same dimension.
Right. Exactly.
I see. And you're getting a function on the real line.
Right. Now,
okay.
This isn't the only way to set this up, but I think this is probably the more stable way of doing defining the intrinsic version.
And it makes it look like a Euler characteristic.
Exactly. So this is the current work, and I think similar injectivity results should hold, but this is, again, needs to be shown. So let me talk a little bit now about the future work. So what remains to be done in this general area? So the first is finiteness results. So thinking back to the PHT and the ECT, the embedded versions, there are these finiteness results that tell you how many directions do you need for an embedded simplicial complex or a planar graph. And it would be nice to have some effective good constants, depending, say, on some geometric features of the graph, which tell you that you only need to sample finitely many directions, or like how fine a sampling has to be to recover the injectivity results. So, and similarly for the IECT, it's a bit premature. I guess first we need to show injectivity results, but yeah, can we get finiteness results? Because again, this is a complicated invariant. It would be nice. It's nice to know that if you sample every point and all the barcodes, you get generic injectivity, but can you get away with only sampling finitely many and still have an injectivity result? The next direction is, so metric graphs are a good place to start because they, in a sense, are very general. I mean, you could take a complicated mesh and take its one skeleton, and that's going to be Gromov-Hausdorff close to the original mesh, but at the same time, you're not capturing any higher dimensional homological information. So how would you generalize this? How would you generalize this to high dimensional objects, maybe a manifold, a metric simplicial complex? And it might be useful to use discrete Morse theory to make the problem more combinatorial, because it's the combinatorial nature of the problem for metric graphs that helps the proofs go through in our paper. So some way to discretize this, say, for a metric simplicial complex, you can imagine generalizing this setup in a number of ways. And can you prove injectivity results for in high dimensions? And the last way in which you could generalize this is, so we've chosen to look at the family of functions that come as distance from base points. But there are other functions that you can define on a metric space. For example, you can look at eigenfunctions of the Laplacian, and you get a family of functions, and you can get in that way a family of barcodes. And as a whole, sometimes eigenfunctions of the Laplacian can be poorly behaved in some stability sense, but perhaps the barcodes might be better behaved in certain settings. And so it would be interesting to understand what happens if you looked at a intrinsic transform based on eigenfunctions, the barcodes of eigenfunctions. Could you still get injectivity results, or more generally, what kind of geometric and topological information does that give you? And so that's another area of future research. So the next slide, I should say, is a bit of a shameless plug, but I'm on the job market, looking for postdoc positions for 2019. So if you're watching this now or on YouTube before that date, and you see any one of the many names that I've attached at the beginning of this, you'll maybe hopefully remember me from this talk. And I put the citizenships in case it's relevant. Sometimes people ask, and that's my website. And And lastly, thank you very much for listening.
Thank you, Elchanan.
And here's all the references. Okay. We may have ended a little less than 50 minutes.
So any questions for Elchanan? So I have a question. So you mentioned Gromov-Hausdorff distance for metric graphs, and then the disjoint union. And it's like, is there anything else? Like, sort of, are there any other topologies that people have looked at that would be of like sort of of interest to that community?
I'm trying to think. So another topology on the space. Well, what alternatives are there to Gromov-Hausdorff distance? So I suppose there are these LP versions of the Gromov-Hausdorff distance, which is sort of an L infinity version. Like it looks at maxes and soups, and you could think about summing or taking integrals. I don't know if that gives you a different topology though. I haven't thought about that, but that is a different metric which could give a different topology. But other than that, I'm not sure. So the topology, this fiber topology would make sense in an applied setting if, for example, you were generating random graphs by first randomly picking a combinatorial type and then randomly picking edge weights, and that kind of probabilistic model would connect with the topology the fiber topology. I guess you could also get topology. I guess I can't really think of any other topologies that of interest.
Okay, great. So in case there are no other questions,
can I ask one more? Or it's fine not.
What did you say,
sure.
Henry?
Oh, can I ask one more question? Yeah.
Oh, yeah, sure. Go for it.
Okay. Feel free to cut me off if I'm taking too long. So the question is, Isaac, you were talking about, of course, finiteness results. Thinking of your version where you're doing this extended persistence where you take the distance from a point. Do you think, so you could ask, what if I only took the distances to a point where those points were restricted to the vertices of my graph? The vertices have degree 3 or larger. Do you think, a class of graphs where you have injectivity by looking only at the vertices, do you think that's a large class of graphs, or do you think that's probably a small class of graphs?
The class of graphs for which the map restricted to the, psi restricted to the vertices is injective?
Yeah.
Well, I mean, that's a subset of, that contains the graphs which are fully injective in Subji.
So I guess what I mean is look at IPHT.
I see.
Where you only look at the vertices of the graph.
So there are little.
How far? Do you think that's going to be injective? Or
so there's two problems I could see. So I thought quite a bit about this. There's two problems. First of all, now you're kind of slightly leaving the space of metric graphs in terms of pure metric information, because you can imagine you could take a metric graph and you could add a bunch of extra vertices along the edges. Now metrically it's the same thing, but now if you're capturing a lot more information. So now to answer that question, you have to be sensitive to not only the geometry but also maybe the choice of the mesh, the choice of how fine the subdivision is. And depending on the subdivision, you'll get a different invariant. Now that could be useful, but it could also obscure things. But in general, let's say that you erased all vertices of valence 2 and just looked at maybe some kind of minimal mesh, some minimal combinatorial model. I think you get a really hard combinatorial problem, and as a whole, it's very hard to, I can't imagine in general how you would prove an injectivity result from that, because you would end up with all these different points in all these different barcodes, and then you would need some test for determining when two vertices ought to be connected by an edge.
Right.
And as a whole, there's not that much information in the IPHT, just on the vertices. And if the graph is very complicated, there's a huge amount of different points moving around, and where they come from is quite ambiguous. So as a whole, even if it were injective, and it might be, I wouldn't know how to demonstrate it.
Right, right.
But I do feel like if the graph is sufficiently complicated, in a sense that there's enough information in there, it should be injective. That's just kind of a hunch. If there's enough rich combinatorial structure, like combinatorial data, you should be able to, recover a lot of information. But how to do it in any algorithmic sense, I don't know.
Thanks.
Sure.
Okay, so I would ask everyone now to unmute themselves so that we can clap for Elchanan. So, yeah, thank you. So we have the next talk scheduled for when exactly, Henry?
The end of the month.
The end of the month. So we're going to see you all then. And thanks again, Elchanan.
Thank you so much,
Bye.
Sarah and Henry. Bye.